The next really important function is the quadratic. Quadratic's so important when you're investigating motion, because any projectile ends up being a parabola. And so knowledge of the quadratic function extremely important for studying motion. Some definitions. So the quadratic polynomial. The quadratic polynomial is just an expression, an algebraic expression. So ax squared plus bx plus c. As opposed to the quadratic function. It becomes a function once we introduce a dependent variable. So in this case, y as it often is. So y equals ax squared plus bx plus c. We've now made it the quadratic function as opposed to just the polynomial. An equation is where, well, instead of making it equal to a dependent variable, we make it equal to a number, and usually that number is 0 when we're solving our quadratic equations. Very subtle differences between the three, but technically that's it. The first one's the polynomial, the second one's the function, the third one's the equation. Okay? If a is 1, if the coefficient of x squared is 1, then it's what we call monic. So it becomes a monic quadratic. Coefficients, well, we know what they are, a, b and c. So they're the bits that go with the unknowns. And you might look at the constant and go, hang on, that's not with an unknown. Well, technically it is. It's actually sitting with x to the power of 0. We just don't write x to the power of 0. Indeterminate, that is the independent variable, right? Because we can't determine what that is. That's what we're substituting in. So we call that an indeterminate. The roots are the solutions to the quadratic. So, or the quadratic equation to be more correct. As opposed to the zeros, they're the x-intercepts of the quadratic function, or another way of saying it is what makes the polynomial equal to 0. Exactly the same as the roots. It's just that we tend to call them roots when we're talking about an equation. We tend to call them zeros when we're talking about the function. But having said that, you'll find we contradict ourselves all the time. And sometimes we call them zeros when we should have said roots. And sometimes we call them roots when we should have said zeros. But they're the same thing. They're the solutions to the equation. So find the roots of x squared minus 1 equals 0. Not really a mind-blowing question there. And we get, oh look, 2 answers of course, plus or minus 1. Never ever get caught out with that. So often people make the silly mistake of just putting positive 1 down. Remember, x squared equals something, you get 2 answers. Okay. Graphing, what are we looking for? Key things, well we know it's going to be a parabola. Okay. So there's our general one, y equals ax squared plus bx plus c. Each of these letters tells us something. A, the coefficient of x squared, there it is, talks about the concavity of the curve. Okay. So if a is greater than 0, we know it's concave up, or happy if you like, because it's positive. So when you're positive, you're happy. So we get a smile. And of course the size of a then tells you how wide the parabola is or how thin it is. And so if it's negative, negative is when we get sad. So we have a frowny face there. A is less than 0, and that's what we call concave down. Concave down. So that's what A tells us. I'll skip B for now. C, well, the constant by itself always turns out to be the y-intercept, because you sub x equals 0 in, you'll get left with the constant. So that tells us the intercept. The zeros or the roots, whatever we want to call them, they're going to find the x-intercepts for us. Now we come to B. B by itself doesn't tell us a heck of a lot. But when we combine it this way, minus b on 2a, that gives us the axis of symmetry. And that's useful because the vertex, of course, always lies on the axis of symmetry. Now, you don't have to use minus b on 2a, because if you've already found the x-intercepts, because of the symmetry of the parabola, you know it's going to be the average of those. It'll always be in the middle. Vertex, well, once I know that axis of symmetry, I can sub in and get the y value. Now that's really useful, because if we want to know the maximum minimum, so you've done some experiment, it's ended up being a parabola, the data, and very often they might say, well, hang on, what's the maximum of this, or what's the minimum could ever happen? Well, you want to locate that vertex. But we're only interested in the y value, of course, we just want the answer. So, well, let's do one. Y equals x squared plus 8x plus 12. Now, I'm not suggesting you would write this down every time. This is just for the sake of the example. You look at, oh, look, yes, A is equal to 1, so I know it's concave up. Excellent. C is 12. So, okay, I might go and plot my y-intercept. There it is, up at 12. The zeros, well, solve the equation. I get, negative 6, negative 2. Let's plot those in. There they are. Axis of symmetry, well, I've got two ways I could do this now. I could use the minus b on 2a. I get negative 4. Or I could just average the two zeros that I've just found. Also, negative 4. Of course, you don't normally draw the axis of symmetry in. I'm just doing it again for the sake of the example. But we know the vertex will lie on that line. So let's find it. Sub in. And we get, by an amazing coincidence, it's also negative 4. Let's plot that point. I think we've pretty much got everything we need now to draw our parabola, because if we know it's going to be a parabola, and we know a parabola is symmetric, I think that's enough to, there we go, draw the sketch. We've got a parabola. So what if we only have limited information, limited pieces of data? All we know are the roots, so all we know are the x-intercepts, and they're 3 and 6. What would the quadratic be? Well, I know it'll be that, straight away. Now, I've done a lot in one step there. I could have gone, oh, I know it's going to be x minus 3, x minus 6, expand the whole thing out. But think back to how you solve quadratics. You always say, what multiplies together to give the last number? So I'm just going back the other way. I'm saying I've got 6 and 3, so I must have multiplied 6 and 3 together. It becomes the last number. And then the middle number, we always say, hey, what adds together to give the middle number? We've got to be careful with that, though, because we've got to change the sign, because when you factorise it, you would have gone x minus 3, and then got the solution x is positive 3. So that's why we change the sign in the middle there. So we add the two numbers together, and we'll get the middle one. I've put a out the front because, well, any multiple of that will give me solutions of 3 and 6. So it could be a multiple. So if I get something like this then, an amazing thing with quadratics is if they are irrational, they always appear in pairs. And those pairs are always conjugates. And so that's real handy knowing this idea, because when you add two conjugates together, the irrational part cancels out. And you just get a nice rational number, 3 and 3, 6. So I get negative 6 in the middle. And of course, when you multiply conjugates, difference of two squares, again, you end up with a rational number. And so I have 7. That is a lot quicker than actually expanding out. X minus 3 plus root 2, x minus 3 minus root 2, and expanding all that out. And that, I mean, it works, but obviously takes a bit of time. Oh, a bit more information now. Oh, sorry, before I do that, notice I didn't multiply it by a, because of the key word there. They told me it was monic. So the coefficient of x squared is 1. So this time, they've given me the roots, but they've also told me what the vertex is. Okay, it'll be some multiple of, add them together, I get 10, multiply them, I get 16. But I know 5, 3 lies on this curve. So if I sub that in, I now get an equation. I can find a, negative 1/3. So there is, I mean, you could expand that out if you wanted to, but well, that's good enough for an answer. All right, number 12 there, you'll notice I use Desmos. She's asking you to investigate some certain things.